me to welcome you another time here.
Okay, yeah.
Longer video.
Yeah, thank you, Flora, for this nice introduction. I think this is the computer I use for the presentation, right? So, yeah. So, I'm giving a talk which is really a talk for lay people. So I assume that you know very little about physics, and I will avoid using formulas because if I put there these glyphs on the screen that you haven't seen before, then you are totally confused and maybe put off. Okay, yeah, but let's start. So, I mean, you may have heard about gravity, and if you haven't heard about that, you feel it daily. And quantum physics, yeah, you may have also heard about that. Many of you have a device that uses quantum physics, like this, the cell phone over there. Well, anyway, the domains of gravity and quantum physics within physics are, well, often quite separate. So they describe different classes of phenomena at very different scales. So gravity acts at a macroscopic scale. We are macroscopic beings, and all these things here that surround us are quite macroscopic. And gravity acts also at very large scales. So it holds galaxies together, the stars and galaxies, and also galaxies form clusters of galaxies due to gravity. So gravity also shapes the universe in this sense. Whereas quantum physics is relevant, particularly in the microscopic domain, and it governs elementary particle interactions. So, well, you may know matter is built up from elementary particles, very small objects. And these very small objects, they interact by three types of forces, basically electromagnetism. Well, electromagnetism, you can see it in some cases. Then there's the weak force that where the particles are taking part in this interaction are, for instance, electrons, neutrinos. This is the force which is involved in radioactive decay, for instance, and there's a strong force which describes, for instance, how quarks are bound together as protons and neutrons and such things. So, and when only few elementary particles are present and come together and interact, then their quantum nature is relevant. There are also then transitions between elementary particles of different type, and that this is possible is also one of the signatures of quantum physics. Now, when very many particles, elementary particles, are found together, then they form macroscopic objects, as you see around you, and they don't display quantum features at large distances, meaning macroscopic distances. So now all types of matter, including electromagnetic radiation, they carry energy. And Einstein, when he invented his special theory, relativity, came up with a formula which expresses that a mass is the same as energy in the context of the theory of relativity. Now, gravity is an attractive force between mass-carrying objects, and it affects actually all objects which carry mass. And by this equivalence of mass and energy, also electromagnetic radiation is subject to gravity because, well, it carries energy, and this equates to mass. And that then means that light is deflected by gravity. And in fact, this is something that one can measure. For instance, if there is a solar eclipse, you can look at the constellations of the background stars behind the sun relative to our line of sight. And you see that this background picture gets distorted when the sun is in the foreground. Well, there would have to be an eclipse, otherwise the brightness of the sun prevents you from seeing the background stars. But if there is, then actually you can very well observe that light from the stars is deflected on its way to us by the gravity of the sun. There's another interesting effect which Einstein has first theoretically derived in his relativity theory, which has later been measured once atomic clocks were sufficiently precise. Namely, clocks have different clock rates depending on gravity. So if you have such a configuration, maybe this second clock there close to the surface of the Earth, and another clock on a very high tower, then the clock in the weaker gravitational field, weaker means it is further distant from the center of gravity, this clock runs faster than the other clock, number 2, which is in the stronger gravitational field, which is closer to the source of gravity. And again, this has also been measured. And nowadays, atomic clocks are so precise and so handy, so that they fit in such a box like this projector, and can carry them around, and then you can measure how the gravitational field changes when you pass over a hill or go around it. So you can measure these variations in the gravitational field using such very precise clocks. Now, one can measure the location and distance between points in space and time using arrays of light emitting and using arrays of devices which emit and receive electromagnetic radiation. So in this case here for the GPS, for instance, radio waves. And your devices here have to be equipped with very precise clocks. So these GPS satellites, they carry atomic clocks on board. They send out signals with their position and with a time stamp, position at the time of the internal clock. And then there are also, for these arrays, some stations which coordinate and synchronize all these signals. And this way you can determine your position on Earth at a given time. So in a way, light signals, as one says in general relativity, together with clocks, suitably arrayed, they are rulers giving you positions. And now, what has to be taken into account in this global positioning system is what I have mentioned. First of all, that light signals or radio signals, likewise, they get reflected in a gravitational field. And the clock rates, they differ. When clocks are in a gravitational field, and also if the satellites are, as they are, in relative acceleration to each other, because they travel on different orbits. So this has to be corrected for, otherwise the GPS will cause significant errors. No? But you can turn this around. You can look at the paths taken by these light rays, or rather rays of radio signals from the GPS. And then you find, well, they are not really straight lines. They are curved. If you form triangles between them, as is done with these GPS satellites, the triangles don't have an angular sum of 180 degrees that you find out. Okay, and that matches with another thing, namely the general theory of relativity by Albert Einstein, who said, well, in this spirit, the effects of gravity can be described as curvature of space-time. So if you have like these maybe 3 satellites with their position x0, x1, x2 on an orbit on the Earth, of the Earth, and you send signals, light signals between them, then the gravitational effects can be described by a curvature, namely the angles of these light rays, they don't add up to 180 degrees. Okay, so Einstein said, well, curvature of space-time is actually what describes gravity. Yeah, so you can then play intellectual games with this. So this is taken from Steven Weinberg's book on gravitation and cosmology. And if you know the Lord of the Rings saga, then you know it plays in Middle Earth. And this is a map of Middle Earth. If you read the book carefully, there is sort of distances given between certain waypoints in Middle Earth, and then you can draw these triangles, and you can check if you measure these triangles, and then you can check, is the sum of the angles 180 degrees, in which case Middle Earth would be flat, or different, in which case the surface of this world would be curved. Well, these distances are often mentioned in the book by the famous wizard Gandalf. And we see Gandalf is really academically trained because he tells you the method of measurement, namely flight time of the crow. Yeah, flight time of the crow. So this is how you can normalize it, because some of the distances are given in miles, yeah, Middle Earth miles, and other are given as the flight time, which is like the time of a light ray from A to B, as our GPS satellites would use. They don't use crows, yeah, so they use radio signals. But that's the same idea. And you see the modern Gandalf would use the GPS. Okay, so anyway, Einstein proposed in his theory of general relativity and gravity that the geometry of space-time, the determination of that used to determine angles and distances, is not determined a priori, but is dynamically determined by the presence of any form of mass and energy, namely in the following way. The effects of gravity, well, they are due to space-time curvature, or in a sense equivalent to space-time curvature. On the other hand, space-time curvature is generated by the presence of mass energy. So there's this picture of the rubber sheet analogy. Higher mass concentration leads to higher curvature. So you see this big ball that sinks in further down to on the rubber sheet, and creates a bigger curvature. And that leads to a stronger gravitational force between mass concentrations. Yeah, so this is how you can visualize that curvature can describe the effects of gravity. And you see how these this actually rectangular coordinate grid gets deformed by putting a mass on it. Okay, so this explains why there are no negative gravity charges in a way, and why gravitational force is always attractive. It also explains why all forms of energy are affected by gravity and why all forms of energy give rise to gravity. Right? So this is this interplay between mass energy and gravity. Now, there are some important consequences and applications. Within Einstein's theory of general relativity and gravity, black holes are a prediction of the theory. So they form when mass concentration is above a universal threshold. This is not so in Newton's theory of gravity. You can avoid this consequence there. But in general relativity, you can't. So a black hole is a completely gravitationally collapsed massive object, which has such a mass concentration that its gravity or curvature is so strong that light cannot escape from the object. There's another consequence of, within the theory of general relativity, that's the cosmological scenario, which is still the paradigm today. The universe has a finite past history and expanded from extremely hot and dense initial conditions. So I will now spend a little bit of time of explaining this a bit more. First, maybe the stellar life cycle. Stars. So first of all, how do stars form? Well, you need some material, a gas cloud maybe. And the gas cloud has denser regions and not so dense regions. And because gravitational force is always attractive, the denser regions, they become even denser. Yeah, they attract more neighboring material and become denser. So they form dense gas clouds, and they become maybe even denser. And when they are dense enough, then the pressure within this cloud by the other non-gravitational interactions starts to increase, and maybe if the density and temperature is high enough, then fusion processes start. This is what gives the energy cycles in stars, in suns like our sun. So, and then the material in the star is fused from hydrogen to ever heavier elements until you reach iron, which has the highest binding energy per nucleon. And well, if you then would want to fuse to higher elements, that would not be exothermal anymore. So first the star heats up, becomes maybe on the upper branch a red super giant, and then it and it has expired its nuclear fuel and can no longer generate thermal pressure from the fusion processes. So what happens is now a supernova will form. So as the star cools, the material now starts to contract again because there's no counteracting thermal pressure. So basically, the outer layers collapse onto the inner layers, and that starts now fusion processes again. So the gravitational potential energy is converted into fusion energy and thermal energy, and then this outer layer heats up so much that it explodes, and it gives an enormously bright stellar event, which is of importance for astronomy, but I won't discuss this. Now, depending on the mass of this remaining core of the star, there are two scenarios. One, if this remnant was sufficiently light, basically less than 4 solar masses, there is a chance for having a neutron star left over, which is stable. This does not collapse anymore. And by the way, this is already a quantum effect, because what keeps the this neutron star from collapsing is the so-called Fermi degeneracy pressure, which is a quantum effect. This Pauli principle is behind it. And so this doesn't collapse anymore. But if the mass of the core is sufficiently large, then the remnant collapses completely into an object that we call a black hole. We don't know what its material state is. We only know the gravitational curvature is so large that it cannot emit any light. So this is why it's called a black hole. So black holes, yeah, so they carry their name because their gravity is so strong that nothing can escape them, not even light. And they have a surface which is called the event horizon. Whenever something enters the black hole, it is trapped in there and cannot get out again. It remains forever behind the horizon for a distant observer. And therefore, considering only macroscopic physics, black holes can only increase in size by having mass or energy falling in. They grow. Interestingly, macroscopically, black holes cannot be split. So this is not an option. So you cannot basically collide two black holes and say, I use this, like in elementary particle physics, perhaps, to now create 5 black holes, maybe. No, that's not possible. So there are theorems due to Hawking and others saying that this is not an option. If black holes come together, they merge to form one larger black hole. Well, I've already said black holes don't emit any electromagnetic radiation. Right. So it came as quite a surprise in 1957 when Stephen Hawking presented arguments that black holes can emit radiation due to quantum effects. And hence, if that is so, black holes can also shrink. Lose mass energy by quantum effects, and that is a scenario that is hypothetical, entirely hypothetical, suggested by Hawking, and referred to as black hole evaporation. I will soon come back to this and explain this in a little bit more detail. Anyway, Hawking radiation of black holes is a very tiny effect, and so far has not been measured. Now, gravity always acts in an attractive manner. So planets don't go away from each other, they like to be close to each other. But that is the case if you have concentrated masses. If you have the situation that energy matter is distributed equally everywhere in space, then in general relativity, it's possible that the energy distribution can also expand. This is not very intuitive, but this is really a possibility in general relativity. And this is the cosmological Big Bang scenario. And it says close to an initial time. We have already, maybe we remember that general relativity basically forces us to having that our universe has a finite past, yeah? Did not have an infinite lifetime. Yeah? So the past was not an infinite time ago, but a finite time ago. So there would have been some initial state of all of the material in the universe. And so here the basically assumption is close to initial time, all energy matter occupies a very small volume in a very hot, very dense, and very symmetric state. Very symmetric means it's everywhere the same, no density or pressure fluctuations. And then it expands gravitationally and cools down like a gas in an expanding container. This is really the picture. It's like gas expanding. So if that is the case, then how come that in this process the distribution of matter and energy does not remain everywhere the same? And over time, stars and galaxy forms with vast empty space between them, because the assumption is, well, initially the distribution was perfectly homogeneous in space, perfectly isotropic, no density deviations from this sort of average value. Well, anyway, then something must have happened. And once the distribution of energy matter is no longer everywhere the same, the denser regions exert stronger gravitational attraction on their surroundings, because gravity is always attractive. And then they become even denser while depleting the space between them. And the origin of deviation from exactly everywhere equal distribution of energy matter, again, lies in quantum effects. Here is a picture which maybe some of you have seen already. This is the cosmic expansion, a sketch of it. Here the time runs from left to right, roughly. And this sort of trumpet-shaped thing there symbolizes the cosmic expansion. So it's like a circle describing the expansion of space at a given time. And well, initially, this bright spot there is this very, very dense and hot state of all the material at the beginning. And you see that is already coming up something that we will soon discuss, quantum fluctuations, and there's also something called inflation. And then this picture gives you the idea that as the time goes on, the space expands and some more pronounced matter aggregations form, some more concentrated bright spots and more black room in between them, more distance between them. Okay, so quantum effects. So quantum fluctuations around a local level of energy, and I'm using an analog here. The surface of a lake. The surface of a lake in this left picture, well, this is really a very improbable picture, but it's supposedly not computer generated, but a real picture from nature. And you see here the surface is totally still. There are no ripples on the surface. You see this particularly well by this mirror image of the background mountains. So this mirror image is almost exactly as the image of the mountain in the background. It's not distorted. So such a situation that this surface is totally still, at the same time actually emitting ripples, but there are no ripples. That is possible in macroscopic physics. It is not possible in quantum physics, as I will explain on the next slide. So what's actually more common is the surface is almost still, right? It's almost still, you don't see big waves, but there are little ripples, and you see them, well, not so well on this projected picture. It's a bit more, it's a bit clearer in the original picture on the slides. When you look at the mirror image, and you see it's a bit distorted, there are little ripples, so you don't have such a nice and almost perfect mirror image as on the left-hand side. So there are little ripples, fluctuations around the totally still configuration. So what does this have to do with quantum physics? So in quantum physics, not all quantities can be determined exactly. This is a slightly vague statement. To make this more precise, I would have to tell you more about quantum physics, which I will not do, but take it as it is. So for some quantities, there are bounds on how precisely they can be determined in statistical measurements. Quantum physics is not a deterministic theory. It's a little bit like statistical mechanics. You only have statistical statements about the quantities of interest. Actually, you would have this also for this distance determination by how the crow flies. If you take an individual crow, it may take very long because it easily gets tired. If you take a different crow, maybe it's in better shape and it does the distance in a smaller time. So you would have to, since you don't know what your crow is up to, you would maybe use 1,000 crows and then take an average and you look at the variance, of this average. So you make a diagram of the time needed by the crows and then get the distribution, and the distribution has a variance. And this is the statistical variance that I'm referring to here. So in quantum physics, for instance, if you measure the variance, the position of something and its velocity, then the product of the statistical variances, this product cannot be arbitrarily small. There is a universal lower bound, which is strictly positive, different from zero. And similarly, the variance in energy times the variance of duration, namely the duration of the variance from the average value, is also bounded below by a universal constant. So therefore, quantum physics fluctuations around a local energy level cannot be avoided. There must always be ripples. They are very, very small. Yeah. So at the macroscopic scale, you don't notice them at all. So to really notice them, you have to go in a lab, measure very precisely, and then you see them. And then you can even make use of them, like maybe in quantum communication, quantum computing, and such things. Yeah, here's another illustration of that. A quantum ball in a bowl can never really be addressed. So if you have a little ball in a bowl, you have the gravity acting, so to speak, from above, then there's a ground state. The ball is really at the bottom of the bowl, but in quantum physics, this is not possible. The ball is always bouncing around a little bit. So it's not, you cannot determine its position and its velocity precisely. This is a statistical statement, really referring to statistical variances. So don't apply this statement too literally, because then you get into trouble. But that's basically the idea. So, and these quantum fluctuations can cause black holes to emit quantum radiation. So we now imagine we are at the surface, at the horizon of a black hole. Okay, so and there are ripples in the quantum photon field. Inevitably, they're always there. So some photons have, for a very short duration of time, a larger energy, denoted by E plus, than the potential gravitational energy at the horizon. So they have a little bit of excess energy. And others, in turn, they have a smaller energy. So they have an energy defect compared to the level of the potential energy at the horizon. And now the gravitational force, if you like, or the curvature at the horizon can cause the smaller energy photon to now fall into the black hole, because it doesn't have enough energy. It has too little energy to be at the place where it actually would have to be classically. And now it disappears behind the horizon. And the other one, then the photon with the excess energy gets freed and carries away this excess energy. Where does this energy come from? Well, it comes from the black hole. So an energy deficit is falling into the black hole and eats up a tiny amount of the energy, meaning the mass of the black hole. Because the energy must come from somewhere. So, and this is the process why one can think, due to this quantum fluctuations, photons can be emitted by a black hole, and in this process would have to shrink because the energy must come from somewhere. Okay. So quantum fluctuations can make the black hole emit quantum photons. And now one goes through this exercise of calculation. This Hawking radiation is a thermal radiation, like a black body radiation. And the temperature of the Hawking radiation is inverse proportional to the mass of the black hole, which is maybe not so intuitive. So the larger the black hole, the smaller the Hawking temperature, the temperature of the emitted radiation. So for a black hole of 10 times the mass of the sun, so this is a so-called stellar black hole, which may have been generated after a supernova explosion by complete collapse. And actually, the gravitational wave measurements, observations in the LIGO detectors, they have given evidence for the existence of black holes in such a mass range. So for a black hole of 10 times the mass of the sun, the Hawking temperature is extremely small, namely it is at 6 nanokelvin, which is 6 divided by 1 billion. Kelvin. So this is extremely, extremely close to the absolute 0 point of temperature, which is in fact very, very close. And this is very much smaller than the temperature of the cosmic microwave background radiation, which is at 2 times 7 Kelvin. So you see this is 500 million in magnitude warmer, even though 2.7 Kelvin is also extremely close at the absolute 0 point of temperature. You would really, I mean, you have to really do something to get close to this in the lab. You can, but it takes effort. So the Hawking radiation of black holes has so far not been observed, and the prospect for observation is slim. But it's perhaps not impossible. One has to be careful saying this is impossible. When I was a student, there was a lot of discussion on conferences about measuring gravitational waves. And it seemed almost impossible. So they thought they were enormously far away from this. And then 20 years later, they succeeded in measuring it. And it's really a success that is based on advances from various different ingredients, from the hardware to the software, so to say. It's quite amazing. And so one should not say that this is impossible. I mean, naively, you would also say it's completely impossible to observe an exoplanet, a planet orbiting a sun many, many, many light years away, because the light that it shines would be far too faint. But then people came up with the idea, well, it's not the light of the planet that you want to observe. It is, so to say, its shadow. Yeah, the way it shadows the light of the star that it orbits. And you can measure this. And it's amazing. So by the order of 1,000, of 10,000 exoplanets have been observed so far. Their orbits, their orbital data can be calculated quite precisely based on these observations. So don't say it's impossible. It may take some time and new ideas, but who knows? So I'm not so pessimistic. Maybe because I'm a theorist, I don't need to bother with how you measure it. Anyway, so let's look at a slightly different and more positive scenario in terms of measurement. So I have mentioned the cosmic microwave background radiation. So what's that? That's an electromagnetic radiation corresponding to a black body at temperature 2.7 Kelvin. And this is a radiation which comes to the Earth from all directions with basically the same intensity, the same spectral temperature. And because it is so almost perfectly homogeneous and isotropic, one thinks that this must be of cosmic origin. And one has made a lot of tests that this really would be the case, and excluded other sources of it. The cosmic microwave background radiation was discovered in the mid-1960s, and its origin was for some time not so very clear. But then over the decades, really the picture has formed that this is of cosmic origin, and other origins have been excluded. So if you read a book on cosmology, then this is usually a major discussion because it is an important observational effect that points at certain cosmological scenarios and excludes others. So, so basically, this radiation is the consequence of the cosmological Big Bang scenario. The universe was initially in a state of evenly distributed, very dense, and very high temperature should be with the energy matter in a small volume. The volume expanded gravitationally. This is important. Yeah, so why did it expand? It expands because of gravity. If it's perfectly evenly distributed, then you can have the case that gravity has an expanding nature, not necessarily a contracting. So the volume expanded gravitationally, thereby cooled down and became less dense. So now we know there must have been tiny quantum fluctuations around the evenly distributed energy matter, the ripples of deviations from the everywhere the same configuration at every given time. So then in cosmology, there's also a scenario which for some independent reasons is favored. It's called inflation. At an early stage, very early stage of the cosmic evolution, the volume of the universe went through a phase of extreme expansion by many, many orders of magnitude in a very, very short time. Well, this would have caused the microscopic quantum fluctuations, the density fluctuations, to become macroscopic. In a similar fashion as these quantum fluctuations being ripped apart by a strong gravitational field, like for the Hawking effect. So, and in consequence, in the then subsequent less extreme cosmic expansion, these macroscopic density fluctuations become more pronounced under gravitational interaction, as I've said, and over time stars and galaxies form with increasingly greater voids in between them. So, well, if this picture of cosmic evolution holds value, then the cosmic background radiation should not be exactly the same in all directions. There should be small directional temperature fluctuations, and these have been observed by space probes that were designed exactly for this purpose, called the WMAP and Planck space probes. And here I have pictures of taken by the Planck space probe. The Planck is the newer instrument, and so it records temperature fluctuations. So if you look at these ellipsoids, they are the celestial sphere projected, and you see, particularly to the sort of North Pole and South Pole, there are dots which are redder and others which are bluer. They signify these temperature fluctuations. Temperature fluctuations are at the order of magnitude of 100,000th of a Kelvin, very tiny. And they are random. This band you see at the equatorial plane is caused by the foreground of the Milky Way, because like ourselves, also the space probe moves in the galactic plane. And if you look at the galactic plane, what you get is mainly the radiation from all the many stars in the galactic plane. So this is a foreground effect. So the directional fluctuations in the temperature of the cosmic microwave background radiation are evidence of an interplay between quantum effects, fluctuations in the density, and gravity, the space-time curvature. and this has been, of course, studied theoretically much more profoundly than I can explain here. So just going through this in detail is basically an advanced lecture in cosmology. I mean, an advanced lecture course of 1 semester in cosmology. Yeah, so this basically ends my presentation up to some remarks. Namely, this presentation up to this point was mostly without any formulas, as you may have seen, equations in relation to mathematics. Actually, this would be needed to make this narrative that I've given quantitative, and in this sense, scientific. So the main mathematical approach underlying these quantum fluctuations of quantum systems like photons or elementary particle physics is to assign to them certain correlation functions relating to their location in space and time that express their properties and also their evolution in space and time. Yeah, these correlation functions have complicated algebraic and analytic structures, and they obey well, fairly complicated differential equations, depending on the geometry of space-time. Again, I mentioned the more complicated the geometry of space-time, the more complicated the differential equations and behavior of these correlation functions. Well, my research project here is actually devoted to the question, can the geometry of space-time be recovered from the analytic and algebraic structure of such correlation functions? So it's basically an inverse problem. As I have suspected from the beginning, but also now I have learned from colleagues here in Paris who are quite specialized in such sort of questions, is that there's also a conceptual problem related to this. And basically, you cannot use information about the space-time geometry to set up the correlation functions, because you cannot put in what you want to get out. So this makes this problem also conceptually quite difficult. And basically, there are some results on this in the literature, but we suspect that the authors have put in what they want to get out. We want to avoid making this conceptual flaw, but it's really a difficult Anyway, people here in Paris are quite expert in the mathematical methods, which we think would be used in answering this question. This is also one of the reasons why I've been here. Thank you.
Thank you very much for this very nice talk. So I must say that